Hello, everyone. It's a pleasure to talk to you once again. We are going to our first talk in the very first day of DPVSA, our school on visual signal processing. And our first speaker is Professor Wen-Hsiao Peng. He is from the Department of Computer Science at NCTU, the National Chiao Tung University in Taiwan. And the title of his talk is Application of Reinforcement Learning to Video Encoder Control and Video Prediction. Professor Peng has a really long story in visual signal processing. He got his PhD from NCTU in 2005. And after that, he worked in the Intel Microprocessor Research Laboratory in USA for between 2000 and 2001. He was where he was involved in development of many technologies, including MPEG-4, considering scalability, fine granularity scalability. In 2003, he has participated in ISO and ITU video coding standardization processes, and he has contributed to the development of many standards, including SVC, HEVC, and SCC. Currently, he is professor at the Computer Science Department at NCTU, and he was a visiting scholar at IBM Thomas Watson Research Center in USA between 2015 and 2016. He's author of more than 70 journal and conference papers, and over 60 ISO and ITU standard contributions. His research interests include video and image coding, deep learning, machine learning, multimedia analytics, and computer vision. Professor Peng has been chair of many important conferences, including VSPC, VCIP, ISPAX, and so on, ICIP, ICME, and ISCAS, of course. He also served as Associate Editor-in-Chief for the digital communication, lead guest editor, and SEB member of the IEEE JetCast. He's also associate editor of TCS-VT and guest editor of TCAS-2. He's also a distinguished lecturer of APSIPA. This is just a very short introduction of Professor Peng, his career. Certainly he can talk a little bit more, but I'm proud to say that he's the chair of VSPCTC, that is one of our technical sponsors, and it's very important to us and for our school. So Professor Peng, the floor is yours. Once again, many thanks for accepting our invitation, and please, you have the word now.
Okay. Actually, I would like to thank Professor Bruno Zet for inviting me to this event. It's a pleasure to be here and to talk with you about our recent research work on applying reinforcement learning to video encoder control and video prediction. Actually, I would like to start my talk with some background information about my university. Bruno, can you see my screen?
I can see your screen. It's on your default. Okay, now I can see the.
Okay, maybe. Yeah. Zoom keep showing error messages saying that I should reduce the usage of my computing resources. I don't know what happened, but I will try. Okay.
But if you keep in this very same layout, it's working fine.
Okay, maybe I should just keep to this mode. So like I say, let me give you a very brief introduction to my university. This is National Chiao Tung University. This is where I'm currently affiliated with. So I guess not everyone know where this National Chiao Tung University is. So basically right now in the world, there are 5 Chiao Tung University. 4 are in China and 1 in Hsinchu and Taiwan. And all at least 5 Chiao Tung universities share exactly the same roots. So our predecessor, Nanyang College, was founded in China in 1896. And then our government moved from China to Taiwan and re-established Chiao Tung University in a city called Hsinchu. So this slide just give you some geographic information about where Taiwan is and also where NCTU is. So Taiwan is actually a very small island. It's right next to the mainland China. And you can see that NCTU right now have a campus in different cities. The main campus is in this city called Hsinchu, which is also home to 500 high-tech company like TSMC and MediaTek in Taiwan. So the main campus is in Hsinchu, and also we have a campus in Taipei, which is the capital of Taiwan. And also recently we created a new campus in the southern part of Taiwan, which is in the city Tainan. And like I say, National Chiao Tung University, or you can say our predecessor was created in 1896 in Shanghai, China. And NCTU was re-established in 1958. And at the beginning, we have only one institute, but over the year, NCTU has evolved into a comprehensive university. And more recently, NCTU will be merged with a medical school in Taiwan. We are trying to develop AI technology for health. So actually, our university has a very strong tie with high-tech industry in Taiwan. For a long time, NCTU has been considered the cradle of high-tech industry leader. For example, I would say 2/3 of CEO and high-level official in our science park are actually NCTU alumni. And these include, for example, the founder of Acer, the chairman of ASUS, and also vice chairman of TSMC. So basically, NCTU has very strong connection with Taiwan's high-tech industry. Okay, so now we have about 1,200 students, and also we have about 700 faculty members, and also 300 researchers with PhD degree. And as you can see from this table, we actually have more graduate students than undergraduate students. So basically, NCTU is a research-oriented university. It's actually one of the top-tier university in Taiwan. So now NCTU has a total of 13 colleges. For example, I'm from a computer science college, and we have college like electrical computer engineering, photonics, and for example, here we have a college of AI and green energy. And I would say almost like half of the student body are students from this computer science college and also this electrical and computer engineering college. So these two areas are our strong suit. So like I say, NCTU is in a city called Hsinchu. Actually, in this city, we have another university called National Tsinghua University. And also, we are just right next to this Hsinchu Science Park. Like I said in the beginning, this science park is home to 500 high-tech companies. And also in this area, we have the largest industrial technology research institute. So you can say that this area is like the Silicon Valley of Taiwan. And also our university has assigned dual degree agreement with 45 schools from around the world. We also have around 400 partner universities. For those partner university, we actually have student exchange programs. So every year we have a student going to our partner university, and we also welcome students from those partner university to do their internship or to become exchange student in NCTU. And also we have over 7 all English graduate degree programs. This include one international graduate program created specifically for international students who want to study in the area of electrical engineering and computer science. So this is a very brief introduction to our university, and I hope that you will have a chance to visit Taiwan and also have a chance to visit NCTU. I guess Taiwan is right now is one of the few countries where people can still enjoy their normal life. So we still have a physical lecture on campus. Okay. Now back to the topic. Here is the outline of my talk today. So I would like to begin with saying, talking about the motivation behind this work. And then I will talk about reinforcement learning basics, just in case that not every one of you is familiar with reinforcement learning. And after that, I will talk about how we apply reinforcement learning to video encoder control and also video prediction. And lastly, I will conclude with a few concluding remarks. Okay, sorry, I guess, yeah, introduction. So actually, my talk try to address one often asked question in the video coding community. That is how modern video codec could benefit from machine learning. I guess some of you probably already know that there are quite a few papers talking about how, for example, deep learning technology can be used to develop end-to-end learn image or video compression. But my talk today deviates from that kind of approach. We try to use reinforcement learning in a modern video codec so that we can actually improve the compression efficiency and also the video quality of modern video codec. So in my talk today, I will present 3 early attempts that try to apply reinforcement learning to video encoder control and video prediction. And the reason why we choose reinforcement learning is that, as you will see shortly, reinforcement learning actually lends itself to dependent decision making with the aim of maximizing a long-term reward. And actually, the application like a video encoder control and a video prediction or extrapolation can be formulated as problem of exactly this type. So now let me walk you through reinforcement learning. So basically, you can see here is the setup of reinforcement learning. So there is the so-called agent, which is the machine we want to train. We hope that this machine can do decision making for us. And then there is the so-called environment. So the whole training process actually starts with the agent taking some action based on observing the state signal from the environment. And then this action and the state signal will be passed to the environment so that the environment will respond with a new state signal for the agent to take its next action. And in the meantime, the environment will also output a reward signal indicating how good the action is. So here, basically, the agent is characterized by this policy distribution. So this policy distribution is actually a conditional probability distribution of action given the state ST here. And the environment is characterized by this transition probability. So given the current state and also the action taken by the agent, basically the environment will output a new state signal and also a reward signal showing how good the action the agent take. So by having the agent interact with the environment, we can actually produce a lot of experience. And each experience is actually a state action reward sequence. So you start with some initial state, and then agent take action A0, and after that, environment will give you a reward signal, which is called R1, and then the agent will receive a new state signal. So basically, the whole learning process iterate in this way. So the whole idea of reinforcement learning is to learn this agent. And now, by having the agent interact with the environment several times, we can generate a lot of experience. And each of these experience is characterized by this state action reward sequence. So for example, E1 actually referred to experience 1. So I have the agent interact with the environment. Then I can generate this state action reward sequence. And I can do exactly the same thing again. And then I get experience 2. And I can repeat the process as many times as I want. So I can actually generate a lot of experience. And as you can see here, each experience, that is each of these state action reward sequence can be described by this joint probability distribution, which is the product of the initial state distribution and also this policy and also the transition probability of the environment. So here we have no control of the environment. So basically, we may not actually know this transition probability, and we do not have any control over the environment. So what we can change is this policy, this conditional probability distribution of action given state. So now we try to optimize the policy in such a way that we can actually assign higher probability to those state action sequence with a relatively higher accumulated reward. So as you can see here, for every experience, we can actually compute an accumulated reward. So we have a different reward here. So different experience get different reward. So we try to optimize our policy so that we assign high probability to those state action reward sequence that give us a larger accumulated reward. So this is the basic idea behind reinforcement learning. And now in this work, in my talk, I will talk about 3 different work. But here, the basic assumption is that I have no knowledge of the environment, meaning that I do not really know this transition probability. So I will try to use the so-called try and error approach to learn this agent. This is also known as model-free reinforcement learning. So we don't really know this transition probability. By the way, feel free to interrupt me if you have any question. So this slide just give you a very brief idea about how we could train the agent from this try and error. So for example, here you can see the implementation of the agent. It's just a function, and it's a parametric function, which is parameterized by this theta. So this agent actually takes state as input, and then it output a probability distribution over a different action, okay? Now, given this experience, starting with the state 0 and also action A0, and then you can have the state, the agent interact with the environment and then generate this experience. So we try to update this function in such a way that if sequence, state action reward sequence, starting with state S0 and A0 will eventually give us a very high empirical, or I should say, will eventually give us a very high long-term reward. Then we should try to optimize the theta so that the agent will take exactly the same action when it see exactly the same state. So for example, here, I try to evaluate the so-called reward to go, which is the accumulated reward starting from this S0 and also A0. So if I found that this reward to go is very good, then I try to update the network parameter here or the function parameter here so that agent will actually repeat exactly the same action when it see exactly the same state. So that's the basic idea of reinforcement learning. So now let me talk about how we could apply this kind of reinforcement learning to video encoder control. I would like to start with the very simple example. For example, here, I will talk about intra-frame coding. So this is no different than image coding. So basically, I encode every video frame individually like images. So the very first step of intra-frame coding is to decompose every video frame into a lot of coding blocks. And then I need to decide how every coding block should be coded. For example, I can have the first coding block be coded very finely so that it has a very good reconstruction quality. Or I can have it coded in a very poor way so that I can save some bits. Okay, so the task here, to put it formally, is to determine the quantization parameter. So you can consider this quantization parameter to be a means to control how every coding block should be coded. So now we have DI and QPI. DI refer to the distortion of, for example, the very first block, and the QPI refer to its quantization parameter. Now I may have a total of capital N block. So I need to decide a total of a capital N QP values so that the distortion sum over all this block is minimized. In the meantime, I can still respect this rate constraint. So for example, you may be given just 100 bits to encode maybe 20 blocks. So you must respect this rate constraint, okay? Now, as you can see here, the challenge is that the decision may, for some block, would affect the subsequent decision for remaining block due to the rate constraint. For example, I can choose to encode a very first field block with high quality. This means that I need to use many bits for representing this very first field block. And because of this array constraint, this also suggests that I may have fewer bits for representing, or you can say for coding the remaining block. So as you can see, the decision you make for the for some of the block will affect the decision for the remaining block. So we have a dependent decision making process here. And also you should keep in mind that every local decision, so every decision you make for every block need to minimize the overall distortion. So we actually have a long-term goal to achieve. And that long-term goal actually corresponds to the total distortion after you encode all the block. Okay, now this slide shows you how we could formulate this intra-frame rate control as a reinforcement learning problem. So I show you again this basic reinforcement learning setup. Now I have the agent play the role of my rate control algorithm. So basically this rate control algorithm need to decide a QP value for every coding block. So you can imagine that we have a total of N block to encode. And now I need to decide a QP value for every block. Like I say, we have a long-term goal to achieve. And that long-term goal is to minimize the distortion over all the coding block. And in the meantime, we have a rate constraint. So you are given only a limited number of bits to represent all these blocks. So the environment here is actually the video encoder. So you can see I try to train a machine learning model so that it can interact with the video encoder many times. And eventually, this machine learning model know how to control the video encoder in a way that can minimize the distortion and also under a rate constraint. So the action here refer to the QP value we choose for every coding block. So once you choose a QP value for a coding block, the video encoder will encode that coding block and then update the state signal and also give a reverse signal to the agent. And later I will give you more detail about how we design the state signal and also the reverse signal. Okay, now let me talk about the terminal state. So basically, you can consider the encoding of all the coding block like a game. So the game need to end at some point. So there are two situations in which the game must end during the training process. For example, the first case corresponds to the situation where the encoder actually successfully encodes all the blocks. But in the second situation, you can see here, maybe the encoder just finished encoding the first capital T block. And then the encoder realized that it used up all the available bits. So in this case, it will encode the remaining block using the largest QP possible. So when you encode the remaining block with the largest QP, basically you use as few bits as possible to represent those remaining blocks. And of course, those remaining blocks will have a poor visual quality. So these are the so-called terminal state. And in these terminal states, we need to examine whether the rate constraint is satisfied or not. And we need to decide whether we should penalize the agent or we should penalize the agent or not. So for example, if the agent have some unspent bits, then we need to penalize the agent so that it will not repeat the same mistake when put into use. And in the other case, when the agent always use up bits all the time, then it will be penalized too, so that it will not repeat exactly the same action. So now let me talk about the state signal here. So like I say, the state signal is the only basis on which action taking is based. So the agent needs to observe some state signal before it can take actions. So let's simply assume here, the encoder have finished encoding the very first block. And now it move on to encode the second block. So in order to decide the QP value, that is how this second block should be coded, we need to compute some kind of state signal. So the state signal should be informative enough for the agent to take right action. For example, here, I try to measure the texture capacity of the current coding block, which is block 2. And I also try to measure the average texture capacity of the remaining block. So this is a kind of look ahead strategy. So I tell you how complex the current block is. And I also tell you how complex the remaining block is, so that you can know at what quality the current block should be coded. So the texture complexity here can include statistics like the variance of pixel value within a coding block, or it can capture information like a gradient. So you can compute gradient at every pixel location, and then you take the average. So the resulting quantity can serve as an indication of texture complexity. So you can think about a lot of different way to compute or to extract this texture complexity. By the way, we try to use the so-called handcrafted feature. So we try to rely on human knowledge with regard to what kind of a feature we should extract here. The reason why we don't use a so-called deep neural network to do the feature extraction is that we are looking at the video compression application. We have the real-time requirement. We simply couldn't afford a very complicated network to extract feature for us. Okay, so this slide actually gives you a more complete list of state signals. So like I say, I will tell you how complex the current block is, and I will also tell you how complex the future blocks are, and then how many bits you still have to use, and also how many blocks you still have to code, and also the frame level initial QP. We actually have a lot more state signal than the list you see here. So now let me talk about immediate reward. So you know, in the basic setup of reinforcement learning, we need to know the state signal. We also need to design a reward signal. So the reward signal is actually the score given to the agent, indicating how good the action is. So basically here, our reward signal is designed to be the negative distortion. So I hope you can recall from my previous slide that we have a long-term goal to achieve. And that long-term goal is the distortion, the sum of distortion over all the coding block. So right after encoding a coding block, I will reconstruct the coding block. I will measure the distortion of that coding block. And then I use the negative distortion as some kind of immediate reward. So this is the immediate reward that will be given to the agent. So once the agent decides a QP value, the encoder encodes the current coding block using that QP value. And then we do the reconstruction so we can measure the distortion. And then we use the negative distortion as some kind of immediate reward. So the negative side here indicate our intent of maximizing the reward by minimizing the distortion. So the reward signal is to be maximized. So in this case, we are trying to minimize the distortion. And also, let's not forget that we have a rate constraint here. So like I say, when you reach the so-called terminal state, for example, if the encoder successfully encoding all the coding block, then we need to check whether the rate constraint is satisfied or not. Or maybe in the process of encoding, the encoder uses up all the available bits. Then we need to terminate the encoding process early. And then we try to penalize the encoder, not the agent, so that it will not take exactly the same action. So this is, there are two cases I want to discuss here. The first case corresponds to the overflow case. And this is the situation where you actually the agent use more bit than it should. And then we have the other extreme case, which is the so-called underflow case. This means that the agent actually has unspent bits. So let's say I give you 100 bits, but in the end you use only 80 of them. Then you have 20 unspent bits. So in this case, the agent will be penalized too, okay? So now this is actually how we design the reverse signal. So this corresponds to the overflow case. So let's simply assume that after coding the first capital T block, the agent found that it used up all the available bits. So then it has no choice but encoding the remaining block with the largest QP value. So all the remaining block will be coded at poor quality. So so at the end of this episode, we will try to encode all the remaining block with the largest QP, and then we measure the distortion. And the sum of this distortion will be subtracted from the immediate reward of the less coding block. In the meantime, because you have to use more bit than you should so that you can finish the encoding of the remaining block with the largest QP. So actually, your actual number of bits will exceed the bit budget. So we need to evaluate how much the resulting bit rate deviate from the target. This become the term in the middle. And the lambda over here is just a hyperparameter. So this is actually the reward given to the less coding block. So basically, at this very less coding block, we need to see whether the rate constraint is satisfied or not. And this corresponds to the overflow case. Okay. And this is another extreme case where actually the agent has unspent bits. So like I say, the agent successfully encode every coding block, but now it has unspent bits. So we also need to evaluate the deviation of between the deviation from the target bit rate. For example, maybe the agent is giving 100 bits, but now it used only 80 bits, so the deviation is 20%. And that 20% need to be considered a penalty and to be subtracted from the reward of the less coding block. So these are how the mechanism we use to design the reward signal. So now let me show you some simulation result. So I guess we finished this work almost 2 years ago. At that time, we trained our agent using only AE sequences because we don't have access to many video sequences. So we just use AE sequence to train our agent. But obviously, the agent would perform much better if you use more training sequences. So these are just common test conditions. These are the conditions we use in training our agent. So here I show you a two figure, and in each figure, the horizontal axis corresponds to the frame index, and the vertical axis corresponds to the bill rate. So this is the intra-frame rate control. So the task here is to encode every video frame at a fixed bill rate. So you can see the horizontal line here corresponds to the target bill rate. Okay, now the blue curve corresponds to the scheme of our proposed method. And the red curve, the red dash curve corresponds to the state-of-the-art algorithm in the standard community software. So now you can see that actually this learning-based agent can perform a rate control pretty well. So you can see every video frame is encoded at almost the same bill rate, and it performs comparably to the best handcrafted design, which is now adopted in HEVC. And the green curve corresponds to the case where you don't do any rate control. So you just encode every video frame using a predetermined quantization parameter. So you can see without any rate control, the bill rate of every video frame could fluctuate quite significantly. So these are two simulation results. One corresponds to the high rate case, the other corresponds to the low rate case. Now, this slide shows you the subjective quality comparison. Surprisingly, we found that the learning-based method can provide subjectively more pleasing result in some sequence. I'm not saying that in every sequence we always show better subjective quality, but in quite a few sequences, we found that the subjective quality is better than the human design algorithm. So the image on the left-hand side is produced by a human design algorithm, and the image on the right-hand side is produced by our learning-based algorithm. So you can see in this area, actually, this learning-based algorithm can give you more details. And also the heat map at the bottom simply show you the choice of QP. So you can see, indeed, this learning-based method determine QP value in a way that are very different from how human design algorithm decide QP value. Okay, and here is another example. I think, again, you can see that the image on the right-hand side can give you some more texture or detail in some areas. And also you can see from the heat map that the learning-based technology or learning-based method does produce a heat map that is very different from the heat map produced by the human design algorithm. Now, let me extend the idea to another similar application, which is called frame level bill allocation. So in the previous case, our objective is to decide a QP value for every coding block. Now, the task here is to decide a QP value for every video frame. So I would say the setting is very similar to the previous case. So here, we need to encode a group of pictures. So let's say we have a capital N, we have a total of capital N video frame to encode. And for each of these video frame, I need to decide a QP value. So basically, the QP value you use will decide how good or how bad a video frame will be encoded, okay? So I would say the setting is still very similar to the previous case. We simply shift the focus from coding blocks to coding video frames. So that's it. But the challenge here is that if you study video compression, you know people use interframe prediction. For example, in order to compress frame A, the frame in the middle, we try to do prediction from neighboring frame. For example, from frame 0 and also frame 6. So frame prediction refers to the idea that we try to subtract, for example, frame 0 from frame A so that we get a residual frame. And then we just send a residual frame to the decoder to save bits. And sometimes we can use more than just one reference frame. For example, you can use both frame 0 and frame 16 to form a predictor of for frame 8. So basically, due to this interframe prediction structure, now the decision of QP value for every video frame become even more complicated. So it's really a dependent decision-making process. So again, this is how we see the problem, the frame level build location problem as an RL problem. I hope it's not that difficult to understand why we design the system this way. So again, the agent is our frame level build location. So this part will be implemented by a neural network. And we try to update the parameter of the neural network so that it can do decision making for us. It can decide the QP value for every video frame. And again, we have the environment. And this environment is just X265 encoder. This is an open source encoder. The reason why we choose X265 instead of the committed software is because this encoder runs much faster. We now need to encode a lot of video frames. So in order to collect enough experiences, we need a very fast encoder. So we have action, we have state, we have reward. Without going into detail, let me just show you some simulation results. So the horizontal axis you see correspond to the GOP index. Like I said, the task is to encode a group of pictures. Now we have a lot of group of pictures in the video sequence. So each of the number you see in the horizontal axis correspond to the GOP index. And the vertical axis is the number of bits you use to encode a group of pictures. So we have two curves here. One is the red curve, the other is the blue curve. So the red curve is produced by X265. So here we try to use the GOP level of bill rate produced by X265 as our target bill rate. So for example, let's look at maybe GOP 12. So if X265 encode GOP 12 with, for example, 15 kilobits, then I ask my agent to encode the same GOP with 15 kilobits. So ideally, this blue curve should match red curve closely. And as you can see, it does. Our method does a pretty good job, even though there's still a small deviation from the red curve. And here we show you the quantization parameter decided by these two different algorithms. Again, the red curve corresponds to X265. And you can consider this red curve corresponds to the so-called human design algorithm. And then the blue curve corresponds to machine learning based algorithm. And you can see these two curves are very different from each other, meaning that the way human decide QP value is really a little bit different from the way how machine decide the QP value. And surprisingly, the machine actually outperform the performance of human in this sequence. So here I show you the overall RD curve. So the horizontal axis is the bill rate, which corresponds to how many bits you use to encode a video sequence. And the vertical axis corresponds to the video quality. So the higher the PSNR value, the better, in general, the better the video quality. So the blue curve is the learning-based algorithm, and the red curve corresponds to the RD performance of X265. Like I said, X265 has its own frame level build location scheme. But now with this reinforcement learning framework, we can actually get an agent that outperforms the human design algorithm. And let's have a look at picture quality. So again, this is a subjective quality comparison. So the image on the right-hand side is produced by our algorithm, and the image on the left-hand side is the baseline, the image produced by X265. So this next slide gives you a close-up view of these two images. As you can see here, the image produced by our algorithm show a little bit more texture detail as compared to the image on the left-hand side. And also, if you look at this background area, again, our algorithm has more texture detail. So I would say the machine does learn how to control the bill rate, and in the meantime, it knows how to improve the picture quality. So this is another example. So the previous example corresponds to a sequence of which has less motion. But for this sequence, we actually has more motion. So now again, you have two curves, red curve and blue curve. So the horizontal axis is GOP index, the vertical axis is the bits. Ideally, the blue curve should match the red curve closely, but you can see there is a gap between these two curves. But surprisingly, we actually found that even though our algorithm uses fewer bits in this GOP, but the picture quality turned out to be better. So I would say the machine really found a better solution than the human design algorithm. So here is the QP chosen by X265 and also chosen by our reinforcement learning-based agents. So you can see they are not very similar to each other. And again, this is the overall RD performance. The blue curve is still above the red curve, suggesting that our algorithm actually outperform the state-of-the-art algorithm in X265. So here is a subjective quality comparison. Again, I give you a close-up view. You can see that the image on the right-hand side actually provide more detail in this area as compared to the image on the left-hand side. Okay, so this is pretty much the very first part of my talk. Now, I would like to switch gear to talk about another application, which is video prediction. Okay, so this application is, I would say, is a little bit different, or you can say it's very different from the previous two applications. So here, the task is to predict future frame from a sequence of past frame. So for example, let's say you are giving frame 1 to frame t. These frames are observable. Now you try to extrapolate future video frame. For example, future video frame from time instant t+1 to time instant t+n, okay? So this kind of video extrapolation or video prediction actually find application in future state estimation for self-driving car or application in video analytics or video compression. So obviously, if you can synthesize a very good future video frame, then you don't need to send any bit to the decoder. So this is just one possible application of this kind of video prediction technology. Okay, so the challenge is that the motion and appearance of video can be highly complex. For example, the object of the scene may move around. The camera itself can also move. So sometimes you will have a global motion. And sometimes the object may undergo deformation. So basically the shape of the object may change over time. And it's also very common that you see a change in lighting condition. And sometimes we even have disocclusion of object, which means that there may be new information showing up in future frame, which cannot be found in the past frame. So this is the so-called disocclusion. So with this, the prediction model, the video extrapolation prediction model still need to capture motion dynamic and also synthesize a clear and a sharp future video frame. This slide just show you one common way to achieve video extrapolation. I would say this is the so-called flow-based video prediction. So actually for every target video frame, which is the video frame you want to synthesize, we try to estimate a displacement vector, which is called motion vector. So for every pixel in a future video frame you want to synthesize, you try to estimate a motion vector. Then you can give an estimate of the pixel value here by simply looking at the pixel value, the value of the pixel pointed to by this displacement vector. So this is just one way of achieving video extrapolation. So you try to estimate a motion vector for every pixel in a video frame that you want to synthesize or you want to extrapolate. So now, given the motion vector of every pixel, you can do so-called motion compensation. You just do warping. You just copy the pixel value pointed to by the motion vector. So this is how you synthesize a future video frame. Now, this slide tells you how we could estimate this motion vector associated with all the pixels in a video frame you want to synthesize. So on the left-hand side, you can see a sequence of video frames. So these video frames are observable. So we try to observe this past frame and then synthesize an optical flow map. So by optical flow map, I refer collectively to all the motion vector for a future video frame. So this is the so-called optical flow map. So normally people learn a neural network, which is parameterized by theta. And then this neural network will accept the past frame, this past frame as input. And at the output, you get the so-called extrapolated optical flow map. And with this extrapolated optical flow map, you can do warping, you can do motion compensation to synthesize a video frame. And normally, they try to learn this neural network by minimizing the distortion between the target ground truth and also the synthesized video frame. And in the meantime, they also normally introduce a regularization loss, which require that the motion vector you generate should be as smooth as possible. So you can consider that you may have two motion vectors associated with two adjacent pixels. Then these two motion vectors should be very close to each other. So this is the second term you see here. Okay. Now, one issue with this approach is that you incur a lot of parameters to estimate. So let's consider a high definition video frame of size 2K by 1K. Then you have 2 million motion vector to estimate. And also it's very difficult to decide a lambda value that can work for all the different type of video signal. So this is the issue with flow-based prediction. So our idea here is to perform motion estimation for only few critical points. For example, instead of trying to estimate a motion vector for every pixel, we try to estimate only few motion vector for only few critical pixels. So here we have only 4 critical pixels. We try to estimate 4 motion vector only, and then we do warping on this sparse motion field. So that's our idea. So this is how we could do it. Let's say you are given a sparse motion field. How are you going to do warping? So in order to do warping, you need to estimate motion vector for every pixel. So now let's consider this green dot where we don't have any motion vector estimated. So if you want to do warping, then you probably want to refer to the motion vector of those critical pixels. For example, pixel 3 is closest to this green dots. So we try to copy the motion vector of pixel 3 to do warping. So if you do it this way, then you are doing some kind of zero order Hall interpolation in the motion field. So this is how we perform warping in a sparse motion field on a sparse motion field. Okay, now the question we need to ask ourselves is how could we get a set of critical points and also their associated motion vector? So this is our idea. So let's say we begin with an initial frame IT. This could be the most recent past frame. Let's simply assume that in some way you get the very first motion vector for critical pixel 1. And then you try to use this motion vector and also this critical pixel to synthesize a future video frame. And after that, you try to concatenate this roughly or crudely synthesized future video frame with all those observable frames. So this becomes the new state signal for the agent to decide what is the next critical pixel and also what its motion vector should be. So this is how we see this sparse motion estimation as an RL reinforcement learning problem. So again, here the agent plays the role of sparse motion estimation. The state signal refer to those path frame and also roughly estimated future video frame obtained in the previous iteration. We use this frame as some kind of state signal, and we hope that the agent can tell us where the next critical point should be, and also what its motion vector should be. And after that, we try to repeat the same process so that we can gradually get those critical points and also their motion vector. So eventually we want to minimize the synthesis distortion. Now, let me just, because I'm running out of time, let me just show you the simulation result. So we try to train an agent on this video data set. For example, we try to train an agent on Kitty data set, and then we test it on the so-called SIF data set. This SIF data set is commonly used for the development of video compression, but only few computer vision experts know the existence of this video data set. So we actually try to use this video data set to test the generalization of our model. So on this table, you can actually find many different baseline methods and many different video extrapolation methods. The very last row corresponds to our proposed method. And we use the mean square error to measure the synthesis quality. We also use the SSIM. And I want to draw your attention to the fact that actually our model is very small. It has only 1 million parameter as compared to maybe 10 million or even 100 million network parameter. I guess I probably cannot show you video here. It may not be easy to really see video. So maybe I can, I don't know. Bruno.
You may try. Let's see if it works.
Okay. Can you see the screen?
Yes, it's working.
Okay, it's working. So now you can see the video produced by our method, which is this one. So some video frame come with a green window frame. Those are context frame. Those are frames that can be observed. And then you have those video frame that come with a red window frame. Those are synthesized future frame. So the video in the middle corresponds to our method, and all the remaining video are the state-of-the-art method. And the ground truth is shown in the top left corner. Okay, so I guess you pretty much get the idea how our scheme works as compared to the other baseline method. Okay, so here I just try to visualize where those critical pixels are. For example, you can see some error on this color map. So basically, this color map shows you the optical flow map. So different color correspond to different motion vector in different orientations. And this black arrow simply tell you where those critical pixels are. So these critical pixels are produced by our neural network. So again, this is another example. Okay, so with this, I would like to conclude my talk today. So I talk about how RL could be useful for addressing dependent decision-making problem, like intra-frame rate control or a frame level bit allocation. So these are the applications where you have a long-term reward to optimize. For example, you want to minimize the overall distortion. And in the meantime, you have a constraint. So which actually make your decision making dependent. So every local decision you make are related to the future decision. And also I explore its potential to video encoder control. I think our model show quite interesting result. And one interesting observation here is that the model need not know the inner working of video codec. The only thing you need to do is to have the agent interact with the environments several times. Then the agent will learn how to control the video codec. And also I discussed one application, one reinforcement learning application to video prediction. So in that work, we actually combine a classic video prediction technique with a IO-based agent. And we show that it's actually more effective in terms of the number of parameters and also the resulting video quality. And I believe we are just at the start of more exploration. And I believe that we haven't really seen the full potential of reinforcement learning in this video area. So with this, I would like to conclude my talk, and I'm ready to take any question you may have.
Professor Peng, many thanks for your inspiring talk. Definitely, reinforcement learning is something that has a lot to be explored and a lot of potential. So thank you once again for your talk. We have a few questions. I'll go directly to them. We have first from Alex. He's asking if you think that this work with reinforcement learning to predict HEVC intra-encoder control can be used for the VVC with equivalent efficiency, or if there are different challenges there. Professor Peng?
Oh, yes, sorry, I need to unmute my mic. Yes,
yeah.
I get the point. So I would say exactly the same idea can extend to VVC, no problem. But the issue here is that I know VVC run very slow. So if you want to learn a very good agent, you actually need a very fast encoder so that the agent can collect enough experience.
Okay, Professor Peng, can you kindly open your camera?
Oh, yes. Let me see.
Then we can talk. Yeah, perfect. Professor Guilherme Correa, that visited you last year, if I'm correct, he's making one question. Hello, thank you for your interesting talk, Professor Peng. I would like to ask you if there's a possibility of the first encoded blocks or the first frames, in the case of frame level control, presenting poor quality because of the agent is not yet completely trained.
I would say my answer to this question is that once the agent is completely trained, we can even have the agent decide the QP for the very first frame. So actually in our case, our agent actually decide a QP value for every video frame, including the very first video frame. So basically the very first video frame is no different than the other frame. But during training, sometimes the agent will make a mistake, but that mistake will be captured by the reward signal. So if the agent found that this reward signal is not very good, then it will not try to take exactly the same action next time.
Okay, thank you. Professor Felipe Sampaio is also making a question here. He thanked for the inspiring talk and brings his question. How video coding prediction applications performance is affected when the proposed reinforcement learning methods are adopted?
Adopted into what?
I'm not sure. How the video coding application performance is affected with these reinforcement learning methods. Felipe, if you are listening to us, you can bring a more specific question also. Otherwise, if you want to try, Professor Peng, answer the question. The question is regarding the performance in terms of compute. I think it's in computing effort. Am I right, Felipe? Yeah, overhead in terms of computing performance.
I guess the computer performance refer to the complexity, right? The required computing resources I would need in order to estimate motion vector one at a time, and then I need to do it gradually, right?
I think this is the question, yeah.
Yeah, I think in our case, you can imagine that we don't really need to estimate many motion vectors. For example, we have done a study on how many motion vectors we actually need in order to achieve the same performance or even a better performance than the state of the art. So surprisingly, maybe for example, like for a video of SIF size, we only need 80 motion vector. Maybe it can be as low as 60 motion vector. So we need to run the iteration 60 times. So we have 60 iteration to 80 iteration, then we are done. So I would say, yes, in terms of runtime, the inference runtime, we do need a little bit longer inference runtime. This is true. Yeah, but this is also like a recurrent neural network. So every time you have a new hidden state and then you generate a new output signal. This is exactly how it works.
Perfect. Thank you. If you allow me, I'll have also a question.
Yeah, sure.
When you are discussing the rate control, we usually have this issue associated to measure quality, especially if you consider there are more important regions inside a frame, the called regions of interest. How could you discuss a little bit on that? Because usually when you are doing a rate control, you can bring more bits to more important positions. Are you considering or planning to consider these sort of regions and how to measure the quality under these sort of scenarios?
Yes, I think if you like to achieve the so-called region of interest-based compression, this is also possible with this reinforcement learning framework. You only need to change the design of the reward signal. Right? For example, if your agent just finished encoding a coding block that happened to be in the region of interest, then you should encourage the agent to do better compression in this area. So you can actually give the agent a little bit higher reward so that it knows that in this area I need to encode better. And also I would say another interesting idea we haven't really explored yet is we probably can replace, for example, the mean square error with any better subjective quality metrics. So it's all about how you design the reward signal. Of course, how you design the state signal is also very important. If the state signal is not informative enough, then the agent doesn't really need to know how to relay its action to the state. So think about the state. Think about the reward signal. You can change the design of the reward signal to achieve what you just mentioned. And even you can change the design of the reward signal to achieve perceptual-based compression. So we are trying to optimize perceptual quality instead of mean square error. And we know that optimizing perceptual quality is much more difficult than optimizing mean square error.
Perfect, thank you for answer. Maybe we can go for a last one, if you don't mind. Mateus is bringing us a question. Is a fade transition as challenging as an abrupt and hard image change for the AI to learn in the reinforcement learning method? I mean, fades are as hard as abrupt sync cuts?
Phase, what do you mean?
Fading, just this smooth transition.
Oh, yes. I think it's okay, as long as you design the state signal well. So I actually don't really talk about how we design the state signal for the frame level bill location application. So actually, in that application, we try to compute, for example, the frame, the complexity associated with each video frame. And also we try to measure the complexity assuming that the video frame is will be coded with interframe prediction. So if you have a fading effect, you can still measure the frame difference as some kind of state signal. And then if your training data include a lot of this kind of video, then the agent should be able to learn well.
Okay. I got Professor Guilherme is asking me just one yes or no question. So this will be the last one. So just to make sure. So it means that the agent is already trained when the first block is encoded, which is because training considers all the blocks to be encoded in an offline-like process, not learned during the encoding. Is that so?
At the inference time, I would say at the inference time, you compute the state signal. And then the agent will tell you what the QP should be for the very first block. We can even evaluate the state signal for the very first block. No problem.
Okay,
right.
I think this is an appropriate answer. I think it's clear now, Guilherme. Certainly would like to hold you for a couple more hours for a deeper discussion. Unfortunately, our program does not allow it. Just thank you once again for talking to us, and also for making it possible to have VSPC on board with us as a technical sponsor. It's really a pleasure to have you as the chairman talking to us here. And just one thing that I have noticed from the first part of your talk, your university has no partners in South America. So this is something to be solved.
Right. Actually, I work in the Office of International Affairs of our university several years ago. Yes, I also noticed that we haven't had any partner university in South America, and I hope that we can work together to make this happen. Yeah,
that would be great, and count on us for that. Professor Peng, so thank you. If you want to give a final message, please feel free. Otherwise, thank you so much for being with us today.
Yeah, thank you. And also I want to thank you for your participation. If you should have any further question, please just write to me. You probably can ask for my email from Professor Bruno Z. And I hope that I can someday welcome you here in Taiwan in NCTU. Thank you.
Thank you. And we hope to have you here in Brazil as soon as this pandemic is gone.